will be reading some papers. This is for, well, clearly my research, and I just want to have a better idea. I think the last time I did this literature review, I was focused on maybe somewhat the wrong thing. I mean, not exactly, but being a bit too specific, looking into how people use MCMC to I guess, I don't know, test the efficiency of MCMC on Bayesian neural networks. But I don't think there's too much on that specifically. So now I'm kind of broadening the scope a little bit to look at how people evaluate Bayesian neural nets in general, and maybe from there, maybe from there we can get somewhere. Okay, so I'll be going through hopefully 5 pieces of work. I think one of which I've read before actually. Actually, I read a couple of these before, but not super carefully. But now I think it's a good time to pay more attention. Okay, so let's see. We have this. We have there's this paper that looks kind of interesting. This one here. Yeah. So this is about, it's like some competition where they, well, precisely look for how different methods quantify the uncertainty. Yeah, so okay, maybe I'll start here first. I don't know. This is also another paper. I've definitely read this one before. Andrew Gordon Wilson and his people. I've read this one before as well. This one is more like a review paper. I've never read this one, but it's actually, I'm pretty glad to have found it. It looks like a nice review, but it's a little bit chunky. It's 35 pages long. I don't know if I can finish it. Yeah. No music today, so just want to focus. So let's go with... Okay, let's go with this one. And then I'm not going to read the full thing, but I'm going to try to get some idea of what's going on. Okay. So you're looking at the traditional losses as well as... Okay. It's a bit too big. Okay. Hold on. Is my mic? Hello? Hello? Is it better? I don't know. Hello? Hello? I don't know what the differences are in these two settings. Wait a second. Advanced audio. Is this better? Is this better? Okay, but I thought I turned the volume, the volume down because I thought I could hear like background noise. So I kinda soften everything, but okay. Let's keep it going. Okay. Wait, let me... Oops. What's going on? Oh. Yeah. this is important. The three main components of the challenge: what is meant by probabilistic predictions, what the format of the predictions are, and the loss functions. Okay. What is this? Okay, yeah. Wait, is it section 2? What did you say? Section 3. Okay, sorry. Yeah. So this is okay. The PDF of the output associated to the test input. The PDF of the output. Yeah, makes sense. So yeah, the density essentially, the target density essentially. So for both cases, you're just looking at, well, you want the target density, right? The first simpler one is to describe the predictive density in a parametric form by means of a Gaussian density function. The predictive mean and variance needed to be specified. In some situations, to allow wait, I'm a bit confused. The first meaning what? Oh, two possibilities are offered. Okay. Okay, for regression we need the PDF and two possibilities are offered. The first one is use a Gaussian, okay, where we need to specify the mean and variance. In some situations, more complex predictive are appropriate. To allow participants to approximately specify any predictive, we allow them to describe it by means of any given number n of quantiles such that okay, imposing avoids that some regions of the output will be given 0 probability, which is unreasonable under the laws we use. Okay. The remaining probability mass equals to alpha 1 plus 1 minus alpha n is accounted by 4 by 2 exponential tails of the form. Okay. So quantiles, I guess it means that you want to just show the different. Yeah, okay. Example where quantiles q.2 equals -2, q.3 equals -1q. Okay. I don't think I necessarily need to do this case. Okay, let's kind of ignore this for now. So you just specify the mean and variance versus. Okay, so this is good because if this is because I was thinking of using actually something like that, which is to take the empirical mixing of the predictions and then finding the variance and then see if how fast they get there. I guess the mean is also important too. So how fast they. Okay, this is interesting. Where should I write it? Okay, let me write it down somewhere. Very good. Loss function proposed. So this is just a standard cross entropy, right? We use 3 losses. the classic average classification error loss. Okay, the negative log probability and the lift loss. The final ranking was established according to the log loss, the two used for comparison. Log loss. So this is, wait, this is classification error though. Log loss. Obtained by thresholding the predictive at 0.5, minimum is 0, obtained when no test examples are misclassified, and blah blah blah. Okay, what is the lift loss? So this is the one that I use. Alright, I mean this is the more natural one anyway. Okay, so I think this is good, because if they are using this to judge the uncertainty, then there's some good sense that what I'm doing is actually very close. Right, so this is just cross entropy. Yeah. So right here, negative cross entropy, maybe highlight for those who need it. Predicting the class of a single test point that actually belongs to class +1. Observe how the loss goes to infinity as the model becomes increasingly certain that the point belongs to the wrong class. Right, okay. Okay, this is correct. So this essentially just means that if it's, well, it is class 1, so if you guess that it is 1 with 100% certainty, you get no loss because you are absolutely correct and you are very confident. That's good. And you know, on the other hand, this means to say that you are very certain it is class 0, and that's wrong. So that means you're wrong and you're confident, which is the kind of the worst case, and you're heavily penalized for this. Okay. Interesting way of using this loss is to give it relative to that of the random uninformative predictor that always predicts 0.5. Okay. If one takes the difference between the log loss of a given algorithm and that of random predictor, one obtains the average gain in information in bits if one takes base log 2 algorithms. Oh, that's an interesting idea. So actually this is interesting. I never really thought about this before. Damn. So this is basically saying that this is one way to evaluate performance of your algorithm, which makes a lot of sense, right? So when you're correct, you don't get punishment, and when you're wrong, you get some punishment depending on how wrong you are. But you need some control in some sense, right? And the control is just kind of the most random guesser, right? So you can imagine just having some algorithm that makes something incredibly, just predicts something incredibly stupid. In this case, it's just always 0.5. So whatever you get is 0.5. But there's a point to it, which is that if this guy does well and you do equally well, then actually your algorithm is kind of useless because it provides nothing interesting than a random guesser. So you want to baseline it to this thing. So if one takes the difference between the log loss, right? So that means you want to this is interesting. I mean, I don't think this is super necessary for what I'm doing, but it is interesting, right? Yeah, because I'm comparing the kind of the difference of the sampler efficiencies. So this factor should cancel out if everything goes well, really. Okay. Haha, since it might be useful to some readers for the other purpose. Hopefully that's more. Lift loss is basically the area under the lift loss curve and is minimum when that area is maximum. We define it in such a way that it is equal to 1 for an average random predictor. Loss is 1. as we will explain, the lift loss is the area lost to the ideal predictor by the evaluated predictor. So this is the part you lost, normalized by the area lost to the ideal predictor. Okay, wait. So the lift loss is the area lost to the ideal predictor. Is the area lost to the ideal predictor by the evaluated predictor. The ideal predictor meaning everything gets correct. Is the area lost? Okay, it's a bit lost to meaning this thing lost. Lost to. Oh no, okay, so this thing gains, right? If you lost to someone, then someone gains something. Okay, cool. The lift lost is the area lost to the ideal predictor by the evaluated predictor, normalized by the area lost to the ideal predictor by the average random predictor. Okay, don't really know what it means at the moment. Need to think a little bit. Okay. I see. Okay, this is actually possibly useful. The curve, which curve is the lift loss of the ideal predictor? Lift k of n, and the line above it is the simple upper bound. The shaded region is the area under the average loss curve of a random predictor. The lift loss is defined as the ratio between the two areas. Which two areas? The numerator is given by the area encompassed by the upper bound lift curve and the lift curve of the predictor being evaluated. The denominator is given by the area encompassed by the upper bound lift curve, and that of the average random predictor. In this way, the lift loss is the area lost relative to the ideal predictor, normalized by the loss of the average random predictor. Nope. I don't understand. Wait, is there any more definitions here? Okay, let me read this very carefully. The curve is the lift. Wait, what is the lift loss? I'm so confused. Okay. It is equals to 1 for an average random predictor. So this area here is the lift loss, which is 1 for random predictor. Is the area lost to the ideal predictor by the evaluated predictor. What? Okay, wait. The curve, oh man, I'm so slow, my brain. The curve is, what's the curve? Is this the curve? It's the lift loss. So this is the lift loss of the ideal predictor. So it is the lowest when the area is maximum. The shaded region under the average loss curve is the average loss curve of a random predictor. The lift loss, wait, and the line above it is a simple upper bound on it. Okay. The lift loss is defined as the ratio between the two areas. So ratio between this and this. The numerator is given by the area encompassed by the upper bound lift curve. So this entire area, and the lift curve of the predictor being evaluated. But where is that? I don't understand. This is the ideal predictor. God damn it. Nice. Getting stuck on the first 3 pages. Very nice. So you have, so you have the upper bound. This is the curve of the ideal predictor. This is the curve of the average random predictor. But where's the curve of the evaluated predictor? What the hell is the ideal predictor really? What is k divided by n? No. Okay, how about let's finish reading first, okay? The lift loss is obtained by first sorting the predictive probabilities yi equals +1 given xi for n test points in decreasing order. Wait, this is binary classification, is it? Is it a binary or classification? I think this is just binary classification, is it? Ah, okay, so binary classification is scalar output regression. Okay, yeah. Alright. So the probability of +1 in decreasing order. What's PSN? Why not just PN? I don't know why. The obtained recording contained in the SIs is applied to the test targets, and K is defined as the obtained reordering contained in the SIs. What does it mean? PI? What's PSI? Oh, okay, so it's a sorted one. Oh my god, okay. The obtained reordering is applied to the test targets. And okay, so you're saying that PS1 should be the most certain that it's class 1. That means hopefully we want to have all the class 1s to be here and all the class 0s to be here and to be everything correct, right? Okay. Such that if it's equals 1, you get a point. If it's not, you get no points. Divided by K. K is what? K is the index. And then divided by n plus is equal n plus this number of test example that belongs to class 1. So divided by the ratio. So you kind of normalize by the ratio and then times n. K divided by n. What is K divided by n? K divided by n, and that L, K is less than 1L plus, because this is at most 1. I mean, this is at most K, so this whole quantity is less than this. That's that much we know. Figure 6 show the blue lift curve, the ideal predictor that would get a perfect ordering. Okay, in the figure we have set n plus equals 0.3, n plus equals 0.3. That means 0.3 30% of all the examples are class 1. K divided by n. For 0 less than k less than n plus, all y's equal plus 1. This means that, wait, what is k? K equals 1 to n. Huh? Is it k the number of positives you guess? I don't know, and therefore the lift loss is equals to 1 minus 13 for kn greater than n plus. Okay, I'm not gonna bother with this. It's a bit confusing. We use two losses to evaluate. Okay, how do we do this? The means of the prediction. The second loss is the average negative log predictive density. So both of these are making a lot of sense actually. We use the NLPD to rank. Okay, so this is kind of like the log loss version, right? So this and this is essentially the same thing, right? Yeah, essentially the same thing. M is the mean of the predictive. Observe that we normalize with respect to the variance of the true targets, predicting the empirical mean of the trained target independently of the test output leads thus to a normalized MSE for close to 1. In practice, of course, we don't know the variance. We simply estimate var empirically by computing the sample variance of the test targets. Okay, so this is the normalized mean squared error, and this is the negative log predictive distribution, the density. Okay, when predicting a single point, the loss up to a constant incurred when predicting at a single point with a Gaussian predictive distribution. In the figure, we have fixed t minus m squared equals 1. And show how the loss evolves as we vary the predictive. Oh, okay. Optimal value of the predictive variance is equal to the actual squared error given the predictive mean. The optimal value for predictive variance is equal to the actual squared error given the predictive mean. Okay. For predictive incurred for predicting input x with true associate target x is given by wait, what the hell's going on? C is a constant independent given m by the optimal value for vi is t minus m, correct? So when this is 1, you get the lowest loss. Wait, I'm confused. Why? The probability of y given x. Oh, Gaussian. Okay, yeah, if it's Gaussian, then this makes sense. Yeah, okay. Yeah, okay, so this is just a long Gaussian. Negative long Gaussian. Oh, but this is negative already. Okay. Okay. Underconfident. Yeah. Okay. Mm. Mm. This is good actually. I'm glad I found this because now I can, whenever I want to motivate it, I can cite these sources as well. Okay, so this is a good point. Have the property of infinitely penalizing predictions made with zero uncertainty. So that means if you are 100% sure and you're wrong, this is gonna be horrific because then you're gonna get something like you're gonna get log 0 here. Oh no, not in this case, or maybe like in this case you're gonna get yeah, you're gonna get log 0, and log 0 is infinity, and that's a problem. Oh, actually, wait. Even this? Really? So let's say y is some value, and then you predict it wrongly with... okay, I see. Yeah, because if you have no uncertainty and then you're wrong, you know, if you get it wrong, then this one will just will blow up. Yeah, okay, so if n data points observed, it might be ambitious to have predictive uncertainty smaller than 1 over n. Okay, this is a bit subtle. So now it says that if it's smaller than 1 over n, it makes no sense because we haven't seen more than that, so you should minimally be that uncertain. Right? I mean, if n... if n data points are observed, let me get my jacket. If you, let's say you see 10 data points, it might be ambitious to uncertainty, so I don't quite understand this. If n data points are observed, okay, it might be ambitious to have... So your uncertainty should be at least 1 over n? Why is that the case? Over n. So let's say you see 10 data points, the uncertainty should be at least 1 over 10. What? One has just not observed enough data to be more confident than that. So oh, this is talking about training data, is it? Wait. I don't get it. Okay. Dim. Okay, so this is the result. Okay. Mm. Okay. Yeah. Okay. 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 choose a different parameter associated with future. This allows Bayesian procedure to learn that one input is less. What? Wow. Okay. Uh-huh. Oh, that's it? Okay. Oh, what the hell is this? Mixture of expert models. Monte Carlo approximation. Okay. Alright, so what did we learn here? What I learned was that beyond the MSE error, it makes a lot of sense actually to look at the log loss, which is what actually I'm already doing here. So I think that's a good sign, right? So log loss, again, just to recap for myself really, more than anything. So the log loss looks like this. So this is just the cross entropy loss really. So I can track this loss to compare the different performances of the algorithm, because idea being we want to capture, well, okay, now this is a bit tricky, because if I'm comparing which say method does better in terms of capturing uncertainty, yeah, then we can say that we can compare the log losses. But if I'm comparing the efficiency of the method, it could be the case, or rather it should be the case, that they are capturing the same uncertainty over time. It's just that how fast do they get there. So essentially I think the log loss should be the same. And then maybe you're looking at a convergence, way of looking at convergence, so that things, yeah, okay, I think I have some idea. Okay, so that's one down. This one, Hamiltonian, Monte Carlo, and VI, variational inference. So they are like kind of like the two popular approach that with kind of differing nature. The Hamiltonian Monte Carlo approach, or just generally the sampling, Markov chain Monte Carlo approach, targets usually the correct distribution and then have a hard time getting there, right? So that's the idea. I target the correct distribution, but to get proper samples or to get good samples, it takes a long time and it's expensive and it's difficult. So that's that. But variational inference does it the other way around, which is that I don't target the actual distribution. I target an approximation of it, but I choose that approximation in a way that I can get there really easily. I can work with that distribution very easily. So the challenges are quite different. So in sampling methods like Monte Carlo, the challenge is to have a sampler that is efficient, a sampler that can be cheaply computed, hopefully, and gives you good sample in a small amount of computation time. That's the goal. And because you're already targeting the real thing, so that's pretty much the only thing that you want to work on, right? Yeah, you just want to have good samples. And for variational inference, we kind of, by construction, we want to have distributions that are easy to work with. So the challenge then is to find a good approximation. It will be an approximation and you will lose information naturally, but you want to find a good balance, right? So something that is easy but actually hopefully close to the actual target. So I guess that's kind of the two methods, how they differ. Okay, blah 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 blah. Okay, blah. Marginal covariance of the target variable. Okay, so that's another way to look at things, which is also something that I think I have some results on that too. marginal covariance of target variable, which can be shown to decompose into two terms. Captures the intrinsic uncertainty in data, aleatoric, and the epistemic. In practice, this and this are readily available from the prediction of model given one particular instance of the parameter. Then Vyx can be computed using the results of different parameters. The trace of the total. Okay, this is a little bit tricky. Okay. Variance of y. So variance of y is essentially right. So actually, what I discussed yesterday was actually correct. Right. Well, okay. Well, I shouldn't say this correct. I should say that it makes a lot of sense. Right. It's very reasonable. So essentially, I'm taking the output. So maybe this weight gives me this output, right? And then as the weight changes, I have different outputs. And then this wiggle here, this is my uncertainty, kind of. And then what I want to do is to find out how fast I can get here. Okay, so this is actually kind of, I mean, in some sense comforting, in some sense not. It's comforting because I have not read two of these works, and I've thought about things on my own a little bit, and they more or less come out to be this kind of very similar conclusions, in fact the same. So that's nice, but it's bad in the sense that yeah, I mean, in the sense that I should probably already know these things and not have to work it out on my own. Okay, so that's this. Yeah, okay, so Hamiltonian Monte Carlo, you just define a Hamiltonian, you do a, yeah, okay, this is essentially my research, more or less. And then for VI, which I guess I place a little bit on, you essentially reduce the KL divergence between your variational parameters. Here you call psi, psi, and then usually you're thinking about a Gaussian, so you're just picking the variance as well as in this case. Okay, I think this is just the mean field way of doing things. Yeah, so the mean field variational method. So you're taking all your variables, making one crucial assumption, which is almost certainly always most likely false, but it's a concession. The assumption is that everything factorizes out in your joint, which means they are independent, or at least I think mutually independent. Yes, and then you can, yeah, so if you factorize everything out, when you do the log, everything drops out nicely, and then you can write things down nicely, and that's kind of the appeal for it. Okay, let's go. So the prior standard normal with small variance, this is interesting. Oh, this is important. I need to highlight this because when I use a huge variance like what I tried, it does horribly. how do I write this down? No, wait, sorry, I should go to here. Initialization state sample from prior. Okay, I didn't do that. I sample from. I use a map estimate. Burn-in determined by within sliding blah blah blah. Samples collected proportional to parameter size. That's interesting. Tuned by running small length chain and observing acceptance rate and performance. Okay, this is important. This is kind of the point that I need to hone in on. Okay, fixed threshold to the loss. Okay. Fixed threshold to the loss. I don't. Okay, I guess this. Yeah. Okay. Yeah. Numbers of samples moderate. Moderate. That's a bit like, you know. I mean, oh, okay, fine, right? I mean, it's something. It's better than saying nothing, right? So I guess it's fine. We perform a comparison in classification performance between HMC VI, MC dropout, and 2-point estimate methods. We found that HMC is subject to the choice, obviously. We tune these parameters and acceptance rate and performance. What's performance? The final choices are blah 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 and blah blah blah. In terms of speed, ML and MAP are the fastest. Okay, VI MC dropout slower and HMC is probably slower. Yeah. The time increased linearly with number of leapfrog steps, of course. One way to improve this is to use stochastic scheme, but you lose the correctness of, or rather you lose the correctness of your, you get some bias basically, I think. Wait, is it bias or is it consistency loss? No, it's not biased, but I think it's not consistent. Yeah. Okay, so what are you comparing? Classification performance. Oh. Oh, I don't really like this. So when they say performance, they're looking at essentially the loss, right? So looking at the loss. But the loss is also some way to measure things, right? The thing that I'm struggling with is whether a low loss correspond to efficient sampler. Not really, right? Not. Not really at all. Not really at all. I think my kind of, or rather, the idea that I'm having, I think it holds up. Oh, okay, that's it. Okay, good. Nice. Short paper. Thank you. Very good. Wait, really? That's really short. Okay. Let's read this part. Okay, so this is kind of a bit like a. Oh yeah, okay, yeah, I get it. Okay, I can buy this. What's the point again? Okay. Yeah, I don't think this is super relevant right now. Test log likelihood. Test log likelihood or the train log likelihood. I don't think it matters, right? For my purpose. Okay. Yes, you see? Yes, oh my god, this is exactly... Wait, I read this paper, but what am I surprised? Did I not read it properly the first time? Okay, yes, exactly. Exactly. Test log likelihood can be misleading. Inference innovations designed to capture structure does not necessarily produce high quality approximations. Wait. High quality as in... okay, let's be careful here. Okay. Yeah. Yes! High test log likelihood is a good way to... is used as evidence. However, we argue that while test log likelihood is a good criterion for model selection, it may not be a reliable criteria for determining how well an approximate posterior aligns with the true posterior, which is true, because it consider the example in figure 1. Okay. Figure 1. Ground truth HMC reveals that has more flexibility than needed. BB produce approximate posteriors that are incorrect. As indicated by the widening in the predictive. BBB, MVG, and BBH produce approximate posteriors that incorrectly have low variance, but all have test log likelihoods that are comparable, if not higher. That's exactly the point. So this paper is actually important. This paper. Okay, this is interesting. Yeah, okay, I think this is an important... Okay, wait. So how did they go around it? Okay. Okay, this is a little bit... This is actually exactly kind of what I'm getting at, I think. So I think, but they're doing it... Okay, it's a bit subtle. Okay. The posterior of your best model reveals regression with mismatch a priori uncertainty. Okay, I think this is important. Okay. So this is saying that even the okay, this is interesting. Well, can we positive predictive distributions? Look at this, evaluating the fidelity is challenging. Yeah. Okay. The more I read, the more I'm actually convinced that what I am suggesting is probably correct. But that doesn't necessarily mean that, I mean, it would be good for my case. But I think being correct is more important than, you know, trying to get something good, trying to get good results. Just get correct first. What? Is that a word, desiderata? Is that a real word? I have a feeling not. Oh shit, it's a word. What does it mean? Something that is needed. Desideratum.
Desideratum.
Okay, maybe I'll try to use that word in my next piece of word. Desideratum. That well calibrated should be both necessary and sufficient to capture variation in data. Okay. Okay, I think I'm convinced. Okay, let's move on. So I read this. What about this? Simple baseline. Oh no, this is irrelevant. Okay, so okay, cool. We are the last one. Wait, let me check on my experiments to see how my boys doing. Still running. Slow. Wait, why is it so slow? Oh, it's almost done. Cool, almost done. Okay, at least one set is almost done. All right, last one. So last one, I'm actually pretty excited. So actually, at this point, I think I more or less know what I need to know, but it's still nice to once in a while read a review paper. Okay, I'm not taking any notes today because just feeling a bit lethargic. I don't know. Blah 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 blah. Blah 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 blah. Okay. What's this? We distinguish point estimate where a single instance of parameter is learned, and stochastic where point estimates without regularization, which simply imply implicit, uniform, and prior, are learned using a maximum likelihood estimator, while point estimate models with regularization are learned with a maximum a posteriori estimator. Bayesian neural stochastic with priors. Okay, I guess. So why is this? Okay, I guess it's okay, I see. I guess it's Bayesian because of the regularization. Even though the regularization can be understood in quite I guess a different way. Blah blah blah. Stochastic activation. Ooh. What? where only a set of weights along with a probability for the activation is learned. So what I'm doing is C, probability over the weights is learned. Okay, I've never actually thought about this. The probability for the activation. What does that mean? That means, I mean, you can definitely just put some parameter in your activation and make it a parameter, I guess. Is that very useful? I don't know. So this is an ensemble learning. Hey, look, I'm doing ensemble learning. Wow, I'm a deep learning person. Yeah. Very good. Very good. Okay. Uh-huh. Okay. Okay. Mm-hmm. 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 Mm. Wait, let me read. As the final prediction when the cost of giving a false positive are equal. Okay, so we need to yeah, I guess. Yeah. No, that makes sense. Yeah, that absolutely makes sense actually. Okay. Well, this is a very friendly introduction. It gives everything in nice, nice explanation. So this is the graphic stuff, right? Actually, I don't remember this. I remember this using this in was it lane Dirichlet allocation, LDA problem. Observe y parameter. This is hyper. What is it? Deterministic functions of other variables. Okay. unobserved variables. Oh, okay, and parameters be plates represented as a blah 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 indicates multiple independent instances of the framed subgraph as a batch B. Okay. Yeah, okay, I mean, I roughly know a bit of these things, but it's not super important here. Okay. This is an important point, actually. Actually, I read this paper, race-based symmetry and scaling symmetry. This basically means if you have some network, you can imagine. Okay, it's a bit hard to describe, but you can essentially mix up the. I think you can either swap two layers or something like that. Yeah, but basically you can. There's some symmetry in the network such that you essentially have multi-modes just due to that symmetry alone, right? We're not even talking about actual having multi-mode, right? So you could have many local maximas, but we're not talking about that. We're just talking about the fact that that symmetry means that you have two sets of solutions or more that give you the exact same outcome, which means that in this Bayesian setting, you don't know, you can't say who's better. So if you're trying to explore both, it's going to be very difficult, and if you explore one, you might get stuck with one, and you can have two analysis that gives you different things, because one's stuck at one stuck at the other. And scaling symmetry is the same idea, right? You can kind of put the scaling in different places, and because they just associate, then it's fine. Then you get this scaling symmetry. Right, okay, so here it is, permuting two rows in the weights. Yeah. That means the more you have yeah. Property. Oh. Oops. This is a good point. Yeah, we could think about constraining things, but it's difficult, or rather, it's expensive, and you don't really care. Not worth our time. What's a givens transformation to constrain the norm? Okay. Right, so yeah, is that the regularization is soft constraint the same as a prior to the posterior? I mean, I guess you can think about it like that. Sure. I don't really need this stuff. MCNC, my bread and butter. Let's just go past that because we know what it is by now, hopefully. And then we have again variational inference. Okay, I don't know what this is actually. Okay. I see. Okay. Okay, so you're doing VI by backpropagation. Okay, I guess. Natural gradient. Okay, empirical base. Yeah, base VI dropout. Stochastic gradient descent. Okay, wait, let me read this part a little bit. Multiplicative noise. Bernoulli noise, okay.
Warm restarts. Okay. Blah blah blah. This one. The one I think my prof is talking about, only on the last few layers. Weights of the non-Bayesian layers should be considered as both prior and variational posterior. Prior and the weights of the non-Bayesian layers should be considered as both prior I don't think I'll be using it in my work currently. Yes. Treating as we go as a prediction. Observe probability or empirical frequency as a function of the predicted probability. If your observed probability predicted is chi-square law. Between the prediction and the true value equal or lower than the actual distance. Oh. Okay. Yeah, I'm interested in this idea. As the probability of observing a variance normalized distance between the prediction and the true value and the true value equals to or less than the actual distance. Okay, so it's a bit like a CDF type of thing. Okay, okay, cool. I mean, all right. So what have we learned overall? We've learned that Qualia Factory is now hosting my stream with 5U. To be honest, I don't know what that means. I'm super new to Twitch. What does hosting my stream means? Like, I'm sorry, I don't, I don't know what's going on. But thanks. I think that's a really good thing, really kind thing that is happening, and I apologize for my ignorance of what is happening. We are here and we want to see real math. Oh, hey, oh, geez, okay. What? Can I get a bit of clarification? What do you mean? Like so like this is. Are you saying you want to see more of this, or that this is not real math? I'm just doing some literature review for my research, really. So, what is happening? What is happening? Yeah, I think it makes a lot of sense. So from this paper, which is Foundation of Math, but it is your choice. Well, I'm completely unaware of your individual backgrounds or your affinity with the subject, but what I am doing is essentially looking for ways to evaluate. Oh no, don't apologize, of course. Oh, cool, Russia, cool. But yeah, so what I'm doing is looking for ways to evaluate Bayesian neural networks. So Bayesian neural networks are essentially neural networks that are learned, kind of through a Bayesian method, and that means to say that instead of learning a fixed set of weights like one would achieve using, Adam or pick your favorite optimizer, in a neural network setting, you get a posterior over the weights, or as I've learned from this work, you could also do posterior over the activations, which is something that I've never tried. Is that? Oh, I guess you can think about. Please, what are you doing? Oh, okay, yeah. So let me repeat again. I'm looking for ways to evaluate Bayesian neural networks. That's briefly what is happening. So what it means is that I have different sampling algorithms which I'm using to learn my, or rather to sample from the posterior over the neural network weights, and I'm looking for ways to, sensible ways to discuss how good each sampler is. And it's a bit subtle in the sense that a lot of the literature out there are talking about how well the methods perform in the sense of high accuracy, confidence interval, that type of stuff, which is fine, but it may not be absolutely appropriate for my purpose, right? So now I'm just kind of reading through some of the existing works out there. This paper is actually useful. It made a good point. It is saying that the issue of model selection should be considered separately from the approximation gaps. But the way they go around this is kind of interesting. So it says that we engineer synthetic data sets to produce well-calibrated posterior predictive, and hence generalization and calibration metrics are proxies for how well a given inference method captures the true posterior. Long story short, it is saying that so if it, I think it shows a plot here. Yeah, so in this case, it's saying that look here. So this envelope, you can see this blue region is the uncertainty of the outputs. Not very good at math. Don't fully understand Bayesian interpretation probabilities. Oh, no, yeah, that's perfectly fine. So the Bayesian interpretation is essentially, loosely speaking, all right, loosely speaking, it means to say that we are looking things from a probabilistic point of view, and what we are interested in is not necessarily any final answer or any final number that we are chasing. We are looking for a final distribution, right? So what that offers is that when we use a distribution, we don't just talk about the values that we can get from that distribution. We can talk about, the mean, the variance, or all types of higher moments, things like that, and that gives us a good sense of uncertainty. Sorry. So if you take a look here, so if we see this picture, for example, let's just consider these two side by side. This means to say that this sampler can generate some values from this region, right? So maybe, if you look at the y-axis, maybe this is something like from 1 to maybe negative 2 to 2, something like this. Okay, and if you look at here, this has a very small envelope. This means that the network will probably give you the output of 0, right? So as you can see, this basically means there's more uncertainty here than here. Now, if you look at what is the center value, if you look at what is the middle value of this envelope, it would be this line. And if you look at the middle value of this envelope, it would be this line. And you can see the two lines look pretty much the same, right? They are, it's the same line more or less. But this tells us something. This tells us that I'm not certain, that I'm not so sure if it's here or here or here or here. It can be just within this range. And why are we uncertain? Indeed, if you look at this here, this says training points here. This means to say where we have data, right? If you have data and you try to plot a line, right, to match the data, right, to try to touch all the data, you get this line. But notice that there's no data here. So there is a chance, right? There's some chance where the actual line could go like here and then go here. So it does make a lot of sense to talk about the uncertainty in this region where there's no data, whereas this method and these methods, for example, they don't do such a good job at that, right? So in a real life example, let's say you see -4 and then you know what -4 corresponds to. You see you have all these data, and now you want to guess at this point what is the value here. At 0, what does it correspond to? A Bayesian neural network output can give you some uncertainty, or rather it does a good job at giving you uncertainty. Maybe it tells you, oh, it's something like -2 to 2, whereas these methods will tell you, oh, okay, it's pretty much 0. And the fact that it's sure, it's a bit problematic because it shouldn't be sure sometimes. I'm good at math, not in neural networks. Oh, okay, well, in fact, the mathematics used in neural networks in my experience is not terribly complicated actually. So if you have a sound mathematical background, just getting exposed to the subject can catch you up to speed really quickly. So if you have not studied neural networks, then naturally this all might sound completely strange and alien. But I guess minimally all you need to know to get started on neural networks is a bit of linear algebra. You need to understand vectors and maybe basically how to do a matrix vector multiplication. And then you need to know how to talk about gradients. Gradient meaning you need to know how to do differentiation with respect to some function, right? So if you remember like dy, dx, that type of stuff, that is how you train a network. And how you work with the network, the math of it is mostly linear algebra. So at the most basic level, that can actually get you quite far. So with just that, you can already code some very interesting experiments. Okay. So here, okay, so we are considering, right, again, so we are saying that what are we saying? We're saying that model selection should be considered separately than calibration, or rather the approximation to the actual posterior. But in this case, they get around that by constructing data sets such that they give well-calibrated posteriors. Therefore, in this case where everything is well-calibrated, then generalization measures make sense. Which is, I guess, it's a nice way of doing things. But of course, then the drawback, I guess it's not a drawback, but a little bit of constraint is that they have to construct their own data set, synthetic data sets, and you know it's a bit less easy to do this. You can't say the same when you're using actual real data sets. Okay, this paper okay. Yeah, this one. Okay. So this is saying the AUC curve is not necessarily very useful because it's determined by the ordering of the scalar predictions. It does not capture anything about the calibration. Okay, actually I believe this. Like, I can believe this. It makes some sense, yeah. So at the end of the day, using the log loss, it's a good way to. Oh, okay, yeah, I think the work I'm doing is largely computational and applied. So yeah, abstract algebra is a very interesting subject that I don't know much about. Yeah, good luck. Hope you find something interesting. I don't see a lot of people doing algebra or math on Twitch, but I hope you find something. Thanks for dropping by. Okay, this is another interesting idea. Even though in my case, I don't think it makes a lot of difference because I'm comparing the differences between the efficiencies of the samplers. So they should all have some type of, in some sense, some constant fixed distance from the loss of the the average uninformative predictor, the random predictor. 0.5. Yeah, actually, numerically speaking, this would just mean deducting something like log 0.5. So I don't think it makes a difference. Okay, this is interesting. And I should really hope that all my samplers give something more than 0.5, right? Otherwise, it'd be random. Or rather, the average loss, yeah. This is not okay. So I think we're done with this. This is useful. This paper, wait. I guess to be safe for my research, I can use a number of combination of them. I could use a log loss. I could use the approximation for the variance. So which is mentioned in this paper, actually using the Gaussian simpler one, is it? Yes. So actually I should probably and then this one is about, yeah, so this is the quantile stuff, but I think I'm gonna stick to this. It's a bit of it's easier to understand and it's easier to compute, and I think overall it is reasonably convincing, so keeping it simple. So what I need to do now is okay, maybe I can switch views here. Full screen. Wait, hold up. Let me move this here. Move this here. Move this here. Then I can probably change to full screen. Whoops. Hold on. Yeah. So yeah, I can't really read the chat, but this is what I'm observing for my code. This is still gonna take like a day to run or something. Item response. Hopefully this is fast-ish. This is still gonna take a little bit. This is not done. And I think right now I'm investigating this thing, which is what I'm doing today here. And it works moderately well, but I don't know. But what I really care about at the end is the mixing. No, this is important. I do not care about the mixing of the cumulative quantities because that doesn't make any sense. What I care about is the mixing of the probabilities. Yeah. And I guess the mixing of the probabilities should be treated individually in some sense, because I can have an example with a lot of uncertainty and another one with very little. If I sum all of them up, which is what I'm doing so far, then I would be losing information about the smaller ones because it would just be dominated by the larger swings. So so technically I am looking at something like n, if I have n data, n number of training data, then I'd be looking at n number of predictive posteriors for n number of data sets. This is tricky. Okay, I guess then might as well we can write some code. Here, does this work? Oh no, it's lagging. Why? Why is it lagging? I don't know. Make it bigger. Oh, whoa, it's a bit too big, sir. Okay. So, yeah, so, wait, why is it all 100? Oh no, I shouldn't use this, I should do this one instead, actually, yeah. So in this case, what I'm looking at, oh, okay, I'm looking at the minimum, which is a bit of a strict criteria. Actually, why would I be looking at the minimum? Should I be looking at the average? No, but minimum is fine because it is just kind of the worst case scenario. If I wanted to, if I could make things, I could use a median to make things a little better. I think. Not very certain. Okay, maybe let me write down. So the mixing, okay, I'm looking for the mixing of the neural net outputs. That makes a lot of sense, right? It does, right? Does it? Yeah, it does. Okay. Wait, why is this running? Didn't I just oh, okay, yeah, I just put this to run a little more. Yeah, okay. This gives me this, and this is the variance, the estimate of the variance. And I'm looking at the distance, but I don't really think I need to do this, right? So maybe I don't need this. Whoops. I think just this is fine. Does this give me an error? Yeah, this is actually okay, right? I mean, let's do 5,000. What am I printing? Okay. Maybe let's say if we take out the first 1,000, what do we get? I'm curious. Oh. Number 6. Pink. Huh. So this has the highest, but I wouldn't really know, right? Would I? Would I really know? Actually, no, I should look at the what is it? The mean? The mean? Should I be looking at the mean? I mean, that's one way to look at things too, yeah. The mean. So the point is, how do I know this is tough. So this is something like the cumulative sum. Yeah, it pretty much is, right? And if I do the variance, then I am looking at the same thing essentially. Okay, this is a bit tricky because after all, I am using sparse chains. That's a problem, right? So I should generate short chains that I could use. Okay, let's do that. Maybe let's do that. So these are done. 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 So let me run a short chain. Maybe that works. Let's warm up and then use like a short chain of say 2000 samples. 1 and well, let's just use 1000 here maybe. So the ablation study kind of gives some results, but now I'm trying to see if I can get something. Oh boy. So with my short chains, oh man. Okay, I think I have to, yeah, I can generate a short chain for this, and there's another one, maybe like a logistic regression problem maybe? Don't know that well. Do I have the results here? The logistic regression problem. The German, is it the German problem? Rosenbrock. Yeah, here we go. Yes. German logistic. Maybe I should run a short chain on this and then yeah, I think that's correct. So in the end, I think a simple idea should be quite good. Oh right, about that. Yes, about that. Should I rewrite some of the code? Let me see. Oh man, do I want to do that? Such a pain. But if I can do a simple logistic regression, actually this would be... Oh, you know what? I'm just gonna do the same thing for Scratch, right? But gonna be logistic. Oh my god. That's it, right? Why do I need to struggle so much with another thing? So I duplicate. Wait, let me check if the server is overrun. Okay, this looks fine. So let me call it linear, well, linear regression, just LR, right? Okay. So I open this up, I keep it here actually. Okay, great. So I have all this stuff, blah blah blah. Okay, now what I need to change is that I don't need this anymore. And then wait, hold on just a minute. Hidden units, I should just call it 1. That's features, and then biases. Okay, so that means to say that I will have 1, and then then I should just come on. Okay, how about I don't even need this, right? I should just cancel all of this, and this would be simply number of features plus 1. Okay, so here. Oh, okay, I should probably put the old code here. Dude, this thing is... Yo, why is it tripping? Okay. I really hope this is supposed to run like super fast. Actually, this is a good idea. I should probably do a few more of these. I have about a little more than a week left to work on this, so it's gonna be tight. So we have the weight, and then we have the bias. The bias is simply the last thing, and then we have these things that don't matter, and then we have these things that don't matter, and then we have this. It's looking very messy now, but hopefully it will clear up a little bit later. So we simply take okay, then we get rid of this, and then we take no, we don't need this, x plus b. That's good. Just wb is fine, and then just wb here is fine. Then get rid of this. I think I'm set. Is that it? Maybe. Oh, okay, that's fast. Let us be a little bit careful and train and see how. Okay, so this is interesting. So the training is not going super well for the test set. Do I expect that? Do I? I don't know. The loss function here. Oh my god, wait, what? This is wrong. Did I screw everything? No, I didn't. Okay, now this makes a lot more sense. Oh my god. Okay. Why is it not going down? Okay, sure. Then maybe let's do something like this. Right? Okay. Param, blah blah blah. Wait. How is this okay? The average loss is 70. That's horrible. Is it not? Wait, let me think. I must be missing something obvious staring me in the face. The labels divided by the labels, the sum. This is just the MSE error, right? Yep. This is equivalent of this. Okay, I didn't do the here. Sample variance of the test targets. Oh, okay. Is this the best it can do? 70? Isn't 70 really bad? And if I train it more, it doesn't go down. That means my network is not expressive enough, right? That's what it means, right? I mean, let me search it up. Yacht UCI linear regression. Maybe linear regression is too stupid for this. Yeah, maybe that's not a good idea. Okay, blah blah blah. Okay. Yeah, technically, if you want to do linear regression properly, you should think about all these model selection things much more carefully than what I'm doing now. Which is absolutely horrible. Well, it doesn't matter, I guess. In my case, as long as they are consistent. What is this? Residual. What? What does this have to do with anything? Wait, let me read carefully. Regression results. Graphs. Show me the picture. Okay. Okay. Oh. I see. Wait. Okay. Three, four, five, six, 7. 1, 2, 3, 4, 5, 6, 7. So, do I get the same values? Not really. Oh, that's because I normalize everything. Should I not? Okay, let's try to not. Maybe that changes things. I don't know. Also, the way I'm normalizing thing is technically wrong. But nah, it's fine. No, I get similar results. That's actually interesting. Oh, it's yes, keep training, my friend. Okay, now it's the same. Oh, because I normalize. Ah. Oh no, that doesn't. Okay, I guess technically I should move this to here, right? Also, did he train on the whole thing? I think this is worth checking, right? Did he train on the whole thing? Oh, he trained on the whole thing. Is that what it is? Yeah, if he trained on the whole thing, then what I have is kind of sensible. But okay, let's just do it right for once anyway. Here, and so here, and then here, and then I can get rid of this line, and then I can do 308. Well, 308, and then I could also do test equals train. Yeah, it's a bit of a hack what I'm doing here, but should work. So number test data. Okay, this is very hacky, but should work. No, maybe I'm using the wrong no, they give me very similar results actually. Okay. Why do I not get the same results? Attributed against the to be regressed against the above attributes. Oh, residuary resistance. Oh shit, I didn't check what I'm really oh no. How do I know what is what? Hold up. Residuary resistance per unit weight of displacement. Residuary what? Oh no, this is correct. Per unit weight of displacement, A-dimensional. Yeah. Well, I mean, I guess I don't have to trust this, but this looks like it's reasonable though. Data. This data should be exactly same as what I have, right? Yeah, it is the exact same thing. Okay, so what's wrong? Yeah, no, this is exactly just the okay, now I'm a bit worried. Like, what am I looking at? What am I doing wrong? What am I doing wrong here? I don't understand. This all looks completely reasonable. It's using everything, yep, and it's training on every data point, yep. Residuals, number of observations 308, yep. And this is the result: 0.19, -6, 4.23, blah blah blah. But I don't get these values, do I? Do I try to normalize my output? Shouldn't matter. Shouldn't matter, I think. Well, it should, but the only thing that changes is probably not a lot. Okay, let me try to get rid of this. Oh, hold up. Blah. Okay, see if this changes anything. Okay. Okay. Train, 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 blah, 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 blah. No, I get the same result, eh? Am I not training low enough? Is that what it is? Five? No. Okay, let me, I don't know. Train, 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 and it goes down. 78.4. Wait, that means my network. What is happening? Wait, what? That means my network output wait a second. Okay, let's just screen the first 10 maybe. Okay, what about the train label? No. Label string. Dude, what is happening? Okay, I mean, it probably means my network is incredibly lame, but isn't that kind of the point? To use maybe I shouldn't make this. Maybe that's the thing that makes the difference? Maybe? It's the same. Yeah, it's the same. What am I missing? Least squares. Least squares. Okay, technically speaking, I have a divide by 2 factor inside, right? But do we really care about that? Right, so this says, yeah, divide by n, that's correct. Alpha 0.035. Okay. don't know what's happening. This is... Wait, what? 2.23, 1.06? Huh? Oh, is it because I never look at my data Y? What the heck? Wait, am I even doing the same problem? Goodness. Yacht hydrodynamics. 1, 2, 3, 4, 5, 6, 7. Why is the data looking like this? Whereas no, yeah, this is correct. 1, 2, 3, 4, 5, 6, 7. No, this is correct. This is correct. Yep. What am I doing with this? Uh-huh. Uh-huh. The last one and the second last one, that's correct though. And then I take the this shouldn't matter, right? The MSC loss that I'm using here. Would this make any difference? I don't think so. Okay, wait, so they say they use 0. What is it? 0 point something. What? 0.035. Let's see if that makes any sense. What? Wait, what? Am I crazy? Wait a second. Oh, what the heck? Why is my linear regression giving stupid results? Am I doing something wrong? What am I doing wrong? Oh, this guy is just wrong. Yeah, that's I mean, that's possible as well, I suppose. But I don't think I'm ready to say that. Yeah, no, that's all this is reasonable. So the coefficient decided is 0.1938, 0.641, 4.23. The fact that there's a negative one, there's a 121 and a negative 19. I kind of log likelihood. Log likelihood. Okay, let me take away the has this anything to do with anything else? I don't think so, but okay. Okay. Let's get rid of this line. Okay, this line is actually a bit dangerous. Uh-huh. Yes. Maybe something like this. Yep. 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 Yeah, no, it's the same result. Oh. Oh. Oh, I did it. Hey, look. Yo. Okay, so point let me just copy blah blah blah. Wait, so it's because I mix up the data? Is that what it is? Oh, that's bizarre. Yeah, so you see, how do I maybe I can pull this out. Okay, whatever. Okay, so you see the values 0.19, negative 7.044. All this matches up with these, which is cool, I guess. So I think it's because I normalize them. Wait, let me try that one more time. So let's say I do this. Okay, it's actually a good sanity check that I'm getting the same answer as a different person. Yeah, okay, so the problem is normalization. So actually, so in this case, this guy isn't doing necessarily the best thing, because when you are not normalizing things, you could, the scale of things could screw up your analysis, because you can imagine if some value goes into the millions and the values goes into like 0.01, then naturally the 0.01 factor is not gonna come out, it's not gonna be represented in the final outcome, which is unfair just because of the scale, right? So okay, no, this is cool. So so essentially I think I'm doing the right thing here. Okay. And that's good. That's comforting, kind of. Wait, am I running short chain experiments now or what? Hold up, I'm a bit confused. Lol. 956. Okay, then I guess I should actually do a long chain experiment first, to do an ablation. So I call it yacht LR. Maybe 50,000 is enough here. And then I'm not gonna sin any person here. This should fly. Yeah, this should fly. Yes. Yes, fly. Yep. Actually, this is nice because then now I can compare the different answers. How many steps is it taking? 30 steps. Okay, that's incredibly reasonable. Okay, cool. Well, for the 3 people viewing and a few from just now, thank you guys so much. I did not expect any of this, so again, this stream is just a way for me to motivate myself to, submit my thesis and get it done on time, essentially. But yeah, because of some of the viewership, I'm actually more motivated to work. I was gonna quit after reading those papers, but now I actually did a few more experiments, and I'm glad to have checked it as well. So thanks for the motivation, even though you might not know that that has an effect. Okay, cool. So I think I'm gonna call it a night, and yeah, I'll be back with more research, and thanks for watching. Bye.